We're now going to take a quick look at the proof for the addition rule of limits of sequences. So this rule says the following. So if the limit of an as n tends to infinity is equal to L, the limit of the bn as n tends to infinity is equal to m, then the limit of the sum of an and bn as n tends to infinity is equal to L plus m. So again, I'm not going to give the entire proof. I'm just going to give you the beginning of the proof. And here it's important to realize that in saying these two things, I know that for every epsilon that's strictly bigger than 0, there exists a capital N1, such that for every n in n, we have that n bigger than n1 implies an minus L smaller than epsilon. I know that I have an n2, such that for every n bigger than n2, I have bn minus m smaller than epsilon. So whatever epsilon I choose here, this holds, and whatever epsilon I choose, this holds. So there exist responses to every epsilon challenge here. And if I want, I can do epsilon 1 here, I can do epsilon 2 here, and I can put in different challenges here. It doesn't really matter. They can all be met. So this we know. So question is, does it follow from this that for every epsilon bigger than 0, there exists a capital N such that when n is bigger than this capital N, then we have an plus bn minus L plus m, put the parentheses here as well, smaller than epsilon. So can we use this to prove that? And here it's important to realize that these epsilons play different roles. Let's take this epsilon and n's here and give them a different color, just to emphasize this. So here, let's call this green epsilon and green n, like this. And our mission now is to say that, well, first, when you start out with him be arbitrary, fixed, but unknown. Our goal is to find this guy. And how do we find this guy? Well, we consider this. So our focus is here. And what are these things? Well, these things are tools, okay? So this is the epsilon I'm given. And then to prove all of this, I have to use my information here in a good way. In particular, I would want to choose this guy in terms of my green epsilon. Maybe he should be green epsilon times 2. Maybe he should be green epsilon half. Something. This would give me an inequality here and here in terms of green epsilon. And if I'm lucky, I can work with this expression here, rewrite it in such a way that this guy and this guy shows up. Then I can apply these inequalities here with, oh, this should be a 2, with the clever choice of epsilon 1 and epsilon 2 that combine into this inequality here. So that's the mission when doing this proof.